So real numbers. So from day 1 to till date, what we discussed, once I will review the concepts, only headlines of concepts. So first class we took the definitions of LCM and HCF, and second one is how to find the LCM and HCF by prime factorization method, and we did some example problems on LCM and HCF. Then we took fundamental theorem on arithmetic, which is also known as unique prime factorization theorem. Then yesterday class we discussed some more two theorems about the decimal expansion of a rational number. Okay. Once again, just I will take a review on that flow chart. Yesterday I gave clearly the flow chart. Decimal expansion of a rational number. Decimal expansion of a rational number. So set of rational numbers are denoted by the letter Q. So the decimal expansion of a rational number. This is the topic which we took yesterday. So every rational number can be expressed in two different decimal expansion: terminating decimal, non-terminating decimal. Means terminating decimal and non-terminating decimal. See, on these terminating decimal and non-terminating decimal, we took two theorems. One is for terminating decimal, one is for non-terminating decimals. So once again I will repeat the two theorems. And here you see the flow chart. Next, again, these non-terminating decimals can represent in two different forms. One is non-terminating recurring decimal, and the second one is non-terminating non-recurring decimals. This is the flow chart. The topic: decimal expansion of a rational number. So from this flow chart, we noted the point: all terminating decimals and all non-terminating recurring decimals are also known as the rational numbers. See, from this flow chart, we gave a different denominators for rationals. See, already you know the rational number definition: a number which can be expressed in the form of p by q, where q not equal to 0 and p comma q are co-primes, which are integers. So other than that, we can define rational numbers means all terminating decimal, all non-terminating repeating decimals, known as rational numbers. To represent rational numbers, Q. We need to use capital Q. Coming to the all non-terminating, non-recurring decimals are known as irrational numbers. So, one more definition for irrational numbers: all non-terminating, non-recurring decimals known as irrational numbers. This is the concept we took from the flow chart: decimal expansion of a rational number. So yesterday we discussed about terminating decimal and non-terminating decimal expansion based on the two theorems, right? Let me revise the two theorems today. So how we are going to take the decimal expansion of a rational number is terminating decimal, or the decimal expansion of a non-terminating decimal given rational number. Let us see. If x be a rational number, with same conditions q not equal to 0, p comma q co-primes, and whose decimal expansion is terminating decimal. If x is any rational number whose decimal expansion is terminating decimal. What is the condition, ma'am? The prime factorization of Q. The prime factorization of Q is in the form of 2 power n, 5 power n. 2 power n, 5 power n, where n and m both are non-negative integers. Non-negative integers. So try to understand here. The non-negative integers means all positive integers including 0. Non-negative integers means what? All positive integers including 0. This is the theorem. So in your text is given theorem numbers like 1.4, 1.5. Just to remember the concept, not about the theorem numbers. If x is a rational number whose decimal expansion is terminating decimal, the condition is prime factorization of Q is in the form of, so clearly I said yesterday also, purely in 2 powers, purely in 5 powers, or in both, where the conditions of n and m are non-negative integers. Here, this is about rational numbers whose decimal expansion is terminating decimal. Coming to the second one, if x be a rational number, whose decimal expansion is non-terminating decimals. Now about non-terminating decimals. The condition of this is the prime factorization of Q. The common point in the both theorems, they give condition about the prime factorization of Q only. That means we don't need to touch that P value what is given in the problem. We have to focus completely on Q prime factorization. So the prime factorization of Q is not in the form of 2 power n, 5 power n. The same conditions where n and m both are non-negative integers. See, if is there any doubt about the non-negative integer, please try to understand. Non-negative integers is nothing but all positive integers including 0. Clear? That means n and m values are all positive integers including 0. Clear? So these are the two theorems. One is about terminating decimal. Rational number whose decimal expansion is terminating decimal. Rational number whose decimal expansion is non-terminating decimal. It should be a terminating decimal means the prime factorization of Q is in the form of purely 2 power m, purely 5 power m, or in both. If the given rational number decimal expansion is non-terminating decimal, the prime factorization of Q is not in the form of this. Not in the form of this means what? The prime factorization of Q contain, other than this 2.5, is there any number as a prime factor? By that we can conclude the given rational number whose decimal expansion is non-terminating decimals. Okay, ma'am? Right. Let us see these two theorems, some examples. One or two examples, let us see. Two different or same examples. Right. The first example 1 plus example 1, 1 by 8. Let us see simple example. Simple number item 1 by 8. Simple. Example 1. 1 If you want to see parallelly, one more example. Let us see second example also at a time. Example 2, 343 by 70. Both the problems you observe. Let us see the first question. 1 by 8. Yes, how they are going to ask the question in paper. Check or verify is the decimal expansion of 1 by 8 terminating decimal or non-terminating decimal without performing the actually division. Without performing the actually division. See, immediately you get an idea when they said without performing the actually division means we have to use both the theorems which we discussed just now. One is about terminating decimal, one is about non-terminating decimal. These are the two theorems which we are going to use when we said without performing the actually division. So now 1 by 8. So let us take the given number 1 by 8. See, both the theorems, the first common point is given condition about Q only in P by Q form. The prime factorization of this Q. What is here Q? 8. So the prime factorization of the 8 is 2 cube. So now you observe the prime factorization of Q purely in 2 power n form. Purely in 2 power n form. So as per our theorem, the rational number whose decimal expansion is terminating decimal, the prime factorization of Q purely in 2 powers or purely in 5 powers or in both is a terminating decimal, right? So now this is purely in 2 powers. That means yes, this is a terminating decimal. In all of you, because the prime factorization of 8 purely in 2 powers. Right. Similarly, you parallelly observe the second question. I took here 343 by 70. Is this a terminating decimal or non-terminating decimal? You have to explain without performing the actually division here also. Okay. Let us take the given number is 343 by 70. The prime factorization of 343 or 70? Which one we are going to write? 70 we have to write. Don't touch this 343 because in both the theorems also they gave condition about the prime factorization of Q. If the prime factorization of Q is in the form of 2 power n, 5 power m, where n and m are non-negative integers, then its rational number decimal expansion is terminating decimal. If the prime factorization of Q is not in the form of 2 power m and 5 power n, is called non-terminating decimal, right? So here we require to write the prime factorization of this 70. So what is the prime factorization of 70? 2 power 1, 3 power 1, sorry, 2 power 1, 5 power 1 into 7 power 1. This is the prime factorization of 70. 2 into 5, 10, 10 into 7, 70. Now we observe. The prime factorization of 70 is 2 power 1, 5 power 1, 7 power 1. If you see, if you take immediately the theorem, if any, the prime factorization of Q is not in the form of 2 power n, 5 power n. Right now, the 70 prime factorization is containing the other than this 2 5, then one more prime factor, that is 7. Can I conclude by this observation is a non-terminating decimal? Yes. If you see students, if you take the theorem immediately after writing the prime factorization of Q, definitely you will say non-terminating decimal. But you see, if you observe a fraction of second, this 7, it can be simplified with numerator. Is it possible or not possible? You observe that before going to take the concept from the theorem. So here there is a chance to do the simplification of this 7 with this 343. 7 ones are 740, 9s are 343. Like this, there is a chance no. If it is not possible, suppose we can't simplify the 7 with numerator, then we can conclude yes, this is non-terminating decimal. Why? Because the prime factorization of 70 is containing the other number as a prime factor, which is 7. That's why it is non-terminating decimal. But before going to say the terminating decimal or non-terminating decimal, is there any possible to do the calculation with numerator or not? If it is possible, do it. So after doing, the simplest line is 49 by 2 power 1 into 5 power 1. Now you see purely this prime factorization of cube in 2 and 5. There is no other prime number as a factor. That's why the given rational number is a terminating decimal. What is the rational number which is given in the question? 343 by 70 is a terminating decimal. So like that, we have to take terminating decimal and non-terminating decimal theorems. Okay, ma'am. Then, so here, first I give question whether the given rational numbers are terminating decimal or non-terminating decimal without performing the actual decimal. Second question, the topic extension. If it is terminating decimal, how we are going to write its decimal value without performing the actual division? Okay, so let us try to write down now its decimal value. 1 by 8 decimal value without performing the actual division. So I got here 1 by 2 cube. So clearly we discussed in the theorem to define the terminating decimal. The theorem says that the prime factorization of cube is in the form of 2 power n, 5 power n. That means purely in 2 powers, purely in 5 powers, are in both. That is terminating decimal. To write its decimal expansion, we discussed clearly. The prime factorization of cube must be in both. Like 2 power n as well as 5 power m. Okay. Here we have 2 cube. There is no 5 power n. Under the condition n is equals to m I said, right? In fact, when we are going to write the decimal expansion of cube, that must be in both 2 power n and 5 power m. Where n and m are equal. When these two are equal, then only it is easy to convert in the decimal expansion. So here I have 2 cube. To make this 2 power n and 5 power m are equal, by what number I should multiply and divide? In that way you think. Here I have only 2 power 3. Means only 2 power n form is there. So I need to create now 5 power m. With the condition n and m are equal. That means I take this 5 power m. With what number I should multiply and divide? Simple. That is 5 cube by 5 cube. If already these two are equal, you don't need to multiply with any other numbers. Clear now? So now,
Q is a prime number. They're asking you.
Q is a prime number. Q is in 2 power n, 5 power m.
Denominator part is to be prime number means
Prime number only, no? 2 is even prime.
Instead of 8, it is supposed to take 13.
Okay. I will take that question also. Right. Let us see this part board. Example 3. If I take question 2 by 13. Okay, ma'am. 2 by 13 is a rational number. Right? Is this rational number is terminating decimal or non-terminating decimal? Without performing the actual division. So we'll take the given number 2 by 13. What is the prime factorization of 2 by 13? 2 by 13 13 power 1. So now we are going to apply the theorem. Both the theorems you see. What is the first theorem? The prime factorization of Q. What is the value here? 13. I written the prime factorization of Q. I got 13 power 1. So now I am going to observe the prime factorization of Q is in the form of 2 power n, 5 power n. Then its decimal expansion is terminating decimal, right? But you see in this problem, the prime factorization of this 13 as 13 power 1 is not in the form of 2 power n, 5 power n. That means what? If the decimal expansion of Q is not in the form of 2 power n and 5 power n, as per the second theorem, the decimal expansion of this question is non-terminating decimal. Non-terminating decimal. If non-terminating decimal, we don't need to write its decimal expansion. 100% there is no chance to ask the question when it is non-terminating decimal, its decimal value. Definitely there is a chance to ask the question if it is a terminating decimal, write down its decimal value. They're not supposed to ask when it is non-terminating decimal value. 100% they won't ask. But if they ask, definitely they will remove the condition. What is the condition? Without performing the actually division. They will remove the condition. If they will remove, we go with the normal division and we have to express the decimal value of this 2 by 13. Clear? Two type of questions. First of all, the question is the given rational is terminating decimal or non-terminating decimal without performing the actually division. Without performing the actually division means use the two theorems. If the given rational number prime factorization in the form of 2 power n, 5 power n is terminating decimal. Other than this 2.5, is there any other number as a prime factor? Non-terminating decimal. If it is non-terminating decimal, 100% there is no chance to ask the question to express its decimal value without performing the actually division. If they want to ask the decimal expansion of non-terminating decimal, definitely they will remove that condition without performing actual division. Okay, ma'am. Here now, continue this problem. Understood all of you? Why I took 5 cube by 5 cube? Afterwards, simplification. 5 cube means 125 by, using laws of exponents, it is 2 into 5 whole cube. So it is 125 by 10 cube. 125 10 cube result how much? 125 by 10 cube result is 125 by 1000, right? Now it is very easy to express decimal expansion. 125 by 1000. So here we have 3 zeros. So already I said yesterday. And we have after the 3 zeros, we have to move 3 steps from 1 place. 1 place digit is 5. So if I move 1 step, 5. For second step, 2. For third step, 1. Then put a point. Still is there any number you write down. Otherwise, put a 0. So finally, what is this decimal expansion? 0.125 is the decimal expansion. Keep it in our mind. Definitely, there is a chance to ask decimal expansion when it is a terminating decimal only. When it is non-terminating decimal, there is no chance to ask the decimal expansion without performing the actual division. With performing the actual division, the division get the decimal value. Okay. Now, look at this question. Already we concluded the given rational number P43 by 70 is a terminating decimal. If it is a terminating decimal, we need to write its decimal value, right? So to write the decimal value, what is the condition now? To write the decimal value, the condition is the prime factorization of Q must be these both where n and m are equal. So if you observe in this, n and m both are equal. Already the both are equal. If both are equal, we no need to multiply with any number. We no need to multiply and divide with any other number, right? That's why simple calculation 49 by 2 into 5 whole to the power of 1. Okay, ma'am. Calculation. What is our calculation for this? 49 by 10 to the power of 1. It's 10. Now, according to our concept, after the 1 we have only one digit. So, move one step from one's place. What is one's place? Is it 9? One step we got, then put a point, then we have 4. So, answer is 4.9. Here, yes, 343 by 70 is a terminating decimal and its decimal value is 4.9. Here all of these two theorems. For any doubts? First of all, they will verify 12 by 6. Huh? Let us see what is the decimal expansion of 12 by 6. Okay, one more example. What is the decimal expansion of 12 by 6? With performing actual division, without performing actual division, let us see. Example 4, 12 by 6. 12 by 6. See, first of all, you try to write down the given rational number 12 by 6, simplest form. If you see the simplest form of this, it's impossible to take decimal expansion. 6 ones are 6 twos are 2 by 1. 2 by 1 is 2 only. So, decimal expansion, why it is required decimal expansion? It's not a decimal number. It is a positive integer which is to even point. What about we can say about the result? 12 by 6 is simplest form first of all. See, you see the question should be is always in a standard form, means simplest form. But you gave the question is 12 by 6. 12 by 6 simplest form. No chance to get simplest form, no? 12 by 6 simplest form is 2 only. It's not impossible to take decimal value. It's not required decimal value. Here, more 5 minutes is there. So still have 10 minutes is there. Attendance. Please submit the attendance sheet. And if you have any doubts, you can ask me now from this class. So one more point I missed. Actually, I need to give some homework from this today's class. Take homework part. Exercise 1.3. So already we completed exercise 1.2. So let's start exercise 1.2. After completing the exercise 1.3, I will go with the activity problems before exercise 1.2. Okay. So in exercise 1.3, supposed to complete the problem numbers 1 and 2. This is your today's homework schedule. Only 1 and 2. I think in each problem is given 3 or 4 questions. So you try to complete these 2 questions in exercise 1.3 in classwork only. Okay, ma'am. So now you ask me if you have any doubts. Yes.